The next thing we're going to talk about is sound waves. So we've been talking about waves that travel along a line, and then specifically waves that travel along a string. But now we're going to talk about sound waves. There are some things that are the same as what we've talked about, and then there are other things that are different. So I want to start by just sort of emphasizing what are the things to look for that are different, what are the things to look for that are the same. So some differences to start with. These are things that are different about sound waves from the waves we've talked about so far. The first one is these are longitudinal waves. Waves along a string are transverse because the motion of points on the string oscillate perpendicular to the motion of the wave. With a sound wave, what's happening is air molecules, or whatever the medium is that the sound is being transmitted through. Let's think of air for now. Say if a sound wave is moving to the right, the air molecules along that path, that horizontal path, are vibrating horizontally. And so since the oscillations are parallel to the path of the wave, it's a longitudinal wave. And you can think of the motion of the air molecules, and you can do calculations with that. We're not going to do that, though, because a more useful measure of what's oscillating as you go along the wave is the pressure. So as air molecules compress and separate, so that's what the oscillations are, you get variations in pressure. And these are variations in pressure that you can measure. The second difference is with a wave on a string, where it's always the same material that it's being transmitted along a string. This can be transmitted through any kind of gas, any kind of liquid, any kind of solid. And some of the characteristics will change. The basic idea is the same for all of these. What you're getting is a longitudinal vibration of molecules that's leading to a change in pressure. And the third big difference between what we've talked about before is, okay, you can get sound waves that move along a line. The way you can think of this is like a sound wave traveling along a tube. And so then the behavior is more similar to what we've seen so far. But usually sound waves are being transmitted in 3 dimensions. And so what happens as a sound wave is transmitted in 3D is that the power from the source is, as time goes by, being spread out into bigger and bigger spherical shells. You can imagine a spherical shell at every time, at every instant, represents how far the wave has traveled at that point. And as that spherical shell gets bigger as time goes by, the intensity is what we're going to measure. The volume of the sound, the energy in the sound at a single location gets smaller and smaller. And that doesn't have anything to do with energy loss or friction or anything like that. It just has to do with the fact that as time goes by, this sound is being spread out more and more. So this means even without energy loss, the sound intensity decreases over time. Okay, so now what are the things? These are the three differences. I think it's helpful to keep these things in mind to understand how this works. Here are the three things, two things that stay the same. The first one is the key distance versus distance equals rate times time relationship. So remember, I wrote that in two ways. The first one was that the wavelength is equal to the wave speed times the period. And then if you replace the period with 1 over the frequency, you can write this in the form that you see more often. Wavelength is equal to the wave speed divided by the frequency. The second thing is the form of the wave function. We're going to have a similar wave function in the case where you have sound just moving along a line. So again, we're going to imagine that as a sound wave moving along a tube. And like I said, well, the wave function for a transverse wave moving along a string gave you the position of a point at a given x location in a given time. And like I said, now we're going to be thinking about pressure instead of the position. But look at the form of this wave function for pressure, and you'll see the similarity. The variation in pressure is equal to the maximum variation in pressure. You can think of that as like the amplitude, but for pressure in this case, times the sine of the quantity 2 pi over the wavelength times x minus 2 pi times the wave speed divided by the wavelength times t. And this is for a wave moving along the positive x direction. And only the signs, the plus minus signs of the terms inside the parentheses change if you're moving along negative x. Okay, so with these two equations, things will look very familiar in the calculations that you can do with sound waves. Okay, let me do an example calculation. Let's say that sound travels along a tube. So here we're talking about motion along a line. The maximum change in pressure, you can think of this as like the maximum gauge pressure that you have due to this sound wave. We're not talking about absolute pressure, we're just talking about how much the pressure changes from the atmospheric pressure. And that's sort of an indication of the overall intensity of this sound, the volume that you hear. And let's say that this is equal to 1.2 pascals. And now let's say that the wave speed is 340 meters per second. This is the speed of sound in the medium. And this 340 is close to what we expect for air. So this is probably air at some slightly different temperature and pressure than we're used to. But this is always the speed of sound. And the frequency of the sound is 220 hertz. The frequency of a sound wave is the pitch. So you'll do a lab related to this where you'll get used to this idea. Musicians understand exactly what I'm talking about here, but a low frequency is like a high frequency is ah, and so that's what the frequency of a sound wave tells you. And we want to calculate the wave function for this sound wave. And we're calculating the wave function for the pressure, and like I said, this is always the gauge pressure. Okay, so all we're going to do is go to the equation for the fluctuations in pressure and try to collect the things that we need to fill out these values. We need a wavelength. We don't have that. We do have a wave speed, and we do have the maximum variation in pressure. So how are we going to come up with the wave length? We're going to use the distance equals rate times time formula. So the wave length is equal to V over F. We know both of these. So this is 340 divided by 220. And that gives you a wavelength of 1.545 meters. And now we can plug this stuff in. The variations in pressure are equal to 1.2 times the sine of 2 pi over 1.545 times x minus 2 pi times the wave speed of 340 meters per second divided by the wavelength of 1.545 meters. Everything's in SI units, so I don't have to worry about the units really. And now just plug that stuff into your calculator and you get 1.2 times the sine of 4.07x minus 1382t. You can tell this has to be, we've done it moving in the positive x direction, because if you give time a small positive number, you need a small positive x in order to keep the stuff in parentheses the same. Now in that example problem, I gave you the speed of sound, but you can calculate the speed of sound. So let's talk about where that comes from. This will be different and depending on the medium that the sound is traveling through. Well, the speed of sound is always greater as, let's say, 4 materials with greater resistance to compression. Stiffer materials. So you can imagine that the speed of sound in diamond would be super, super high, whereas the speed of sound in air is fairly low because there's this slackness. If you compress one part of it, it takes a little time for that compression to translate to the thing next to it. And V is smaller for materials with greater density. Density is mass per volume. So you could imagine the speed of sound is going to be greatest for something that's very stiff and very light per volume. Maybe think of something like titanium that's a very stiff metal, but it doesn't have a lot of mass for a given volume. With this, so the speed of sound is calculated as the square root of capital B divided by the Greek letter rho. And the meanings of these things, B is called the bulk modulus. That's the stiffness that I was talking about. And that tells you how much pressure is required for a given change in volume. For a given volume change. And so think about what that means for a second. If you have something that's very stiff, then for a given volume change, you need a huge amount of pressure to achieve it. If something is not stiff, to achieve a given volume change, you don't need much pressure. So that's the meaning of this. The SI units for bulk modulus are pascals, the units of pressure. And then this Greek letter rho is the density. And so this is equal to the mass per volume. And so the SI units for the density are kilograms per cubic meter. Let's do a couple of calculations. These are values that you're going to use all the time. So as an example, what's the speed of sound for, first, let's do it for air. And I'm going to do, so this will change for air based on the atmospheric pressure and the temperature. But we're going to use standard atmospheric pressure and room temperature. And the resulting bulk modulus is 140 times 10 to the third pascals. And the density of air is 1.20 kilograms per cubic meter. And then we're going to calculate the speed of sound in water. The bulk modulus for water, well, think of how easy it is to compress water. Water is often treated in calculations as if it's totally incompressible, so you expect this bulk modulus to be really high. And it is 2.10 times 10 to the ninth. So 1,000,000 times bigger, well, not quite, I guess, but many thousand times bigger than the bulk modulus for air. And the density is also quite a bit higher, about 1,000 times higher. Okay, so for air, the speed of sound is 140 times 10 to the third divided by 1.2 square root. And with these numbers, you get 341.57 meters per second, say 700 miles an hour or something like that. That's pretty close to the value that that we'll consider to be the normal, which is 343 meters per second. And then for water, plug in the values, 2.10 times 10 to the ninth divided by 1,000. Take the square root, and you get 1449.14 meters per second. So if you're trying to transmit a sound signal, you'd rather be, and you're trying to get it to your to the observer quickly, you'd rather be transmitting it through water than you would for air. It's almost 5 times as fast through water as it is for air. Now talking about the volume of the sound, the amount of energy in that signal. We're going to talk about power, intensity, and then decibels. And like all waves, sound waves transmit energy through space. And the rate at which that energy is transmitted is the power. One thing I want to point out is when I'm talking about pressure, scroll up here, I'm going to be using a lowercase p. And when I'm talking about power, I'm going to be using clearly uppercase P. I'm going to put a little thing on the bottom like that to try to emphasize it. So don't get pressure and power mixed up. They're both going to be coming up in this discussion. But power is the energy transferred per unit time. The SI units for power, we've already talked about this, but it is joules per second, and that has units of watts. Power is a very useful way to talk about energy transfer when you're talking about motion moving along a line. But for a motion that's spreading out in 3D space, where the amount of power at each location is getting sort of smaller and smaller as your envelope of this sound motion, this sphere, is spreading out. And so a more useful measure, a more useful quantity for this wave that's spreading out in 3D is intensity. I'm going to use a capital I to represent that. And that is the power divided by the area. The area that we're going to be dealing with is always a sphere, so we're going to be talking about the surface area of a sphere. So this is power divided by the surface area of a sphere is 4 pi r squared. So for a given distance r from the source, the intensity is from this formula. Now, intensity, if we're trying to figure out the volume, the amount of energy that we're hearing at a single location in space, the intensity is really what we want. The one complication is that there's a huge range of intensity values that are meaningful to people. The range of intensities that your ears can process is much larger than the ranges of other things that we're used to. And so this decibel scale was designed to make this kind of a more common looking range of values. So ears can process a huge range of intensities. The smallest intensity that we can hear is 10 to the minus 12. I didn't give the SI units. Let's pretend I did. SI units for intensity would be units of power, watts, divided by units of area, that's meters squared. Okay, so ears can process a range of intensities from 10 to the minus 12th watts per meter squared to about 10 to the positive 2 watts per meter squared, and that's where you experience pain from a sound. And that leads to the decibel scale of intensity. I'm going to use the capital Greek letter beta to represent decibels. And so beta, the definition of the decibel scale is beta is equal to 10 times the log base 10 of the intensity divided by that sort of base value of intensity, which is going to be 10 to the minus 12th. Okay, remember I said that's the intensity where you first can hear a sound. So to use this decibel scale, it's very helpful to remember a few rules of logarithms. So let me give you a little refresher on that. Okay, so the first thing is if you have the base 10 logarithm of some value x times some value y, so if you're multiplying two things together, this is equal to the base 10 log of x plus the base 10 log of y. Okay, so if you have all this stuff in the logarithm, you can split it into the sum of two separate logarithms. Similar thing for division. So log base 10 of x divided by y is the base 10 log of x minus the base 10 log of y. And then the third thing is if you have the logarithm of some value x, and you want to know what that is, so we'll just give that a name y. This is equivalent to the equation x is equal to 10 to the power of y. That's what that means. Okay, so one thing I want you to notice about this that is that means you can see that in the definition of decibels, we're going to always be subtracting the log base 10 of 10 to the minus 12, you know? So what is the log base 10 of 10 to the minus 12? That's going to be a really helpful thing for us to know. Let's set that equal to y. And what that says is that 10 to the y is equal to 10 to the minus 12. And so y is equal to minus 12. Okay, we're going to use that in our calculations. Okay, let's do an example calculation using this decibel definition. Let's say we want to know what's the intensity in watts per meter squared of 90 decibels. Well, using the definition, 90 is equal to 10 times the base 10 log of the intensity that we're trying to calculate divided by 10 to the minus 12. Right away, we can just divide out the 10. So we have 9 is equal to the base 10 log of I over 10 to the minus 12. And now we can start using these rules. This is equal to the base 10 log of the intensity that we're looking for minus the base 10 log of 10 to the minus 12. And so 9 is equal to the base 10 log of the intensity. The log base 10 of 10 to the minus 12, I just said that that's equal to minus 12. So we're subtracting minus 12. So this is plus 12. So this says negative 3 is equal to the base 10 log of our answer. And now we're going to use that equation definition. This equation is equivalent to saying 10 to the minus third is equal to I. And okay, so I is equal to, well, 10 to the minus third. And this is in watts per meter squared. So there you go. That's how to go back and forth between intensity and decibels. Now let's combine the relationship between power and intensity and do another example problem. So let's say that a power source, a sound source, has a power of 525 watts. How many decibels is the sound 30 meters away from the source? Well, we're 30 meters away, so our R is going to be 30 meters. And now we can use that with the intensity definition. So the intensity is going to be the power divided by 4 pi times 30 squared. And that gives an intensity of 0.0464. And now our decibel level is 10 times the base 10 log of 0.0464 divided by 10 to the minus 12. So 10 times the base 10 log of, just divide those out and you get 4.64 times 10 to the 10th. Plug that into your calculator and you get a decibel level of 106.66 decibels. 525 watts is a lot, and so 30 meters away you still have a very loud sound. The last thing that we need to talk about related to sound waves is the Doppler effect. And the Doppler effect says that if you have, you always have a sound source and you have an observer of the sound. If either one or both of those two has some velocity, if they're moving, it changes the observed frequency. So if a sound source is emitting a sound at 100 hertz, and the source and or the observer are moving, then the observed frequency is going to be something different than 100 hertz. In order to understand how that works, why it happens that way, imagine an observer. Okay, so here's the observer. He loves the music he's listening to. And imagine a sound wave coming towards this person this way at the speed of sound. Okay? And imagine that the way the person detects this sound, the frequency of this sound, is their brain measures the time for one period of the sound. Okay? And now imagine that this same sound wave is coming towards the person, but the person is running toward the sound wave, okay? Now, what's the amount of time that the brain is going to detect between when those two peaks of this wave hit the ears? Since the person is running towards the sound, it's going to be less time between these two than it was when the person was still. And so this person moving toward the source detects less time between peaks, and the result is that the observed frequency is greater. The same thing happens if the source is moving towards the person. If the source is moving away from the person or the person is moving away from the source, the exact opposite thing happens. The brain detects a larger amount of time between these peaks, and the observed frequency, the experienced frequency, is lower. Okay, so the formula that that lets us do these calculations for different speeds and things like that is that f prime, the observed frequency, that's not a derivative, that's just saying a different frequency than our what we're going to call f, is equal to the speed of sound in the material plus the velocity of the observer divided by the speed of sound in the medium minus the velocity of the source. And you can think of this as a multiplication factor that you're multiplying by the actual produced frequency. Okay, so let me just tell you what each of these things are. V is the speed of sound. If the sound is traveling through air, that's the speed of sound in the air. If it's traveling through water, that's the speed of sound in the water. V0 is the velocity of the observer. Where positive is a velocity toward the source. And Vs is the velocity of the source, where positive is toward the observer. And then finally, F is the, well, let me say F prime is the observed frequency. And F is the produced frequency. So let's do an example problem. So let's say that there's a source that's at rest and it produces a sound at 310 hertz. And let's say that first the observer moves toward the source at 20 meters per second. And the medium that the person is detecting this sound through is air. And then second, we're going to do this calculation with the observer moving away from the source at 15 meters per second. And the medium in this case is water. And for the speed of sound in these two media, I'm just going to use the values we've come up with before. So I'm going to use 343 meters per second for air, 1449 for water. Okay. So for part A, the observed frequency is 343 plus 20. The source is not moving, so the denominator is just 343. And then we're multiplying that by the produced frequency of 310. And we get a value of 328.08 hertz. So the person observes a higher frequency than was actually produced. For part B, the observed frequency is, now we're using the speed of sound in water, so 1449. The observer is moving away from the source. That means that we have a negative velocity. The source, again, is at rest, so that's just 1449 times 310, the produced frequency. And we get a value of an observed frequency this time of 305.72 hertz. So this time when the observer is moving away from the source, the observer picks up a lower frequency than was produced. This is the effect that you hear when an ambulance goes by, say, as it's coming towards you, it sounds like a higher pitch. When it reaches you and moves past you, it becomes a lower pitch to your ears.